Okay, so good morning. It's a beautiful day outside. So I hope you enjoyed the exam paper, right? It was very easy. And so starting should be easy, right? Next time, we will see. Anyway, so we were looking at hash functions. It's a beautiful topic, or message integrity. And, in the last class, because there's a large gap here, right? So I just want to recall what we were looking at. So we were trying to construct these hash functions. Why do we need hash functions? If there is a text and we want to check the integrity of the text, right? Or whatever, some data, right? So we have some sort of hash function. So normally x is our text and y is equal to some function h of x is our hash value. And then we actually, send this thing x comma y pair to, any receiver or whatever. And so one can compute, the y. So whatever, suppose x is tempered, so you will get x prime and you compute the hash value, so it will be different. So that means you know that there is some tempering in the data. So the question is, how do we design these hash functions so that they are secure? So we were talking about security of the hash functions, and we talked about three problems, right? If you recall, I'm going to again look at briefly some of those things. And uh, if we can solve those problems, then basically we can break the crypto system, right? I mean, we can break, we know that our hash function is weak, basically. So to make strong hash functions, these problems should be difficult to solve. Now, again, using probability or the probabilistic arguments, we can try to analyze these three problems. And the last one, which is collision resistant, is very, very important one. And under certain assumptions, normally people see that if it's a collision resistant, so then the previous two problems of pre-image problems are, also safe, basically. So so I think we did two algorithms, and we also gave you some idea about the Las Vegas algorithm, if you remember, right? Randomized algorithms. We talked about those things. So those things will analyze. And so finally, I will show you that there is one very popular thing is known as birthday problem, right? So you will see that that kind of attack is possible, or when it is possible, right? So under these probabilistic arguments, we can show you certain things. So basically, bottom line is that we should have certain bits to make sure that that kind of breaking is not possible. So we should have, say, maybe 160 bits is minimal, right? Or more than that. Okay. So for some of the popular ones like MD5 or SHA1, SHA2, so they have assumed, okay, if we have these many bits in the output, then we are sure that it is secure. Okay. So I'm going to first do this analysis, and towards the end, I'm going to talk about iterated hash function. Iterated hash function when the domain is infinite. Okay, so initially we have defined it for the finite domain, but when the domain is infinite, we are going to talk about iterated hash function. So today I'm going to give you a general framework of iterated hash function, and in the next class, that is tomorrow 8 o'clock, we are going to discuss the specific construction there. Okay, so that is the idea. Okay, so I'm just recalling this hash function. Hash function is this, right? So there are two kind of hash functions: keyed hash function and unkeyed hash function, right? So you know, so normally this x comma y pair is sent, right? X is our message and y is the hash of x, which is h of x. Okay, that function, or hk of x if it is a keyed hash function. So formally, a hash family consisting of a set of possible messages, capital X, a finite set of possible message digest or authentication tags or tags. K is the key space, and for every key in key space, there is a hash function HK. Now the size of X could be finite or infinite, but size of Y is always finite. Okay. under these conditions, this function is known as compression function. Okay, so we talked about these things. I'm just recalling few basic facts. Okay, so the idea is, so we have this hash function. Now we look at the security of this hash function. So we defined three problems. The first problem, pre-image, a hash function h from x to y is given, and a point y in y is given. Point an x such that h of x is equal to y. Okay, if this is the pre-image problem. Okay, so a hash function for which the pre-image cannot be solved is a one-way hash function, or we say that it is a pre-image resistant. Okay, yes. That's the condition for the compression function. Compression function. No. So basically, what I'm saying that here I'm just looking at the pre-image. Okay, I want to find the pre-image. In fact, I'll talk about, as I mentioned earlier also, right? So for example, there are different ways we can look at the problem. The first is first pre-image, second pre-image, and then also the collision assistant, right? I'm not doing anything new. Whatever we have done last time. Okay. Second pre-image problem, a hash function h from x to y and x is in x, point another point x prime in x such that, which is different from x such that these two points coincide, the hash function coincides, right? So this is a second pre-image. So first pre-image is difficult to solve, second pre-image is difficult to solve, right? So a hash function for which second pre-image problem cannot be solved efficiently is second pre-image resistant. Okay, and the third one is collision resistant. So if hash function h from x to y is given, point two points x and x prime which are distinct in x such that their hash value is same. Okay. So I think I will show you towards the end. In fact, I will not show you, but I will just mention that the proof is, I'm skipping the proof, that if a function is, if a function is collision resistant, then the previous two problems are also under certain conditions, are safe. So basically, so we should worry about collision resistant things, and that will ensure that the first two problems are also taken care of, right? So anyway, so this collision resistant problem is an important one. Okay. Now, in order to analyze these three problems, we look at random oracle model, in which we have oracle access. Okay. So a hash function h is chosen randomly from this whole collection, and we are only permitted oracle access to the function h. The only way to compute hx is to query the oracle. Okay, so it is a look, that is the oracle access of the hash function, and then we have this result, and using this result, actually we arrived at. In fact, anyway, so I think we need to look at what are these algorithms that we are going to look at. So randomized algorithms, they can make random choices during their execution. A Las Vegas algorithm is a random algorithm that may fail to give an answer, but if also gives a but if algorithm does return an answer, then the answer must be correct. Okay. Okay, so that is a randomized algorithm, or the Las Vegas algorithm. Las Vegas algorithm is a randomized algorithm. So actually, these two parameters are important for our analysis. A randomized algorithm has worst case success probability epsilon. If for every problem instance, the algorithm returns a correct answer with probability at least epsilon. And a randomized algorithm has average case success probability epsilon if the algorithm returns a correct answer averaged over all problem instances of a space size is at least epsilon. Okay, so these two probabilities we can compute actually for the randomized algorithms actually. So let me give you the first algorithm. Algorithm 5.1 is known as find pre-image. So h is given, hash function is given, a point y is given in y, and q. Q is how many queries you can do the oracle. So choose any x naught to be a subset of x, and total size of x naught is q. For each x in x naught, if hx is equal to y, then return x, otherwise return failure. Okay, this is a very basic algorithm for finding pre-image, right? So I think I have shown you the average case success probability for this algorithm is 1 minus 1 minus 1 by m raised to power q. Okay, so so we have already done this proof. So now the second algorithm is point second pre-image. Okay, so y is going to hx is assigned to y. Choose x naught to be a subset of x minus that point x. So total size of x naught is q minus 1. For each x naught in x naught, if hx naught is equal to y, then return x naught, else return failure. So this algorithm also we have done last time, and the success probability of this algorithm is 1 minus 1 minus 1 by m raised to power q minus 1. So from today, I am going to start this collision algorithm. So algorithm 5.3, point collision. So h is given and q is given. How many queries you can make to the oracle, and h is the hash function. So now I need to find 2 points, right? So now choose x naught to be a subset of x, and number of queries are q in x naught. For each x in x naught, what we do? We assign hx to yx. If yx turns out to be yx prime for two distinct points x and x prime, then return the pair x comma x naught, else return failure. Again, all these are very, very basic things, but I think you can actually compute the probability here. So let me show you. So before actually discussing this, we are going to do some discussions about birthday paradox, right? So which is important one to analyze similar thing. So in a group of 23 randomly chosen people, at least 2 will share a birthday with probability greater than half. Okay. So suppose domain is set of all living humans, and for every x in this domain, h of x is the birthday of a person x. Okay. And range of h is 365 days. Actually, this will be 366 days for those when you look at those kind of years, otherwise it is 365. So if this is given, right, and I want to find out. So finding 2 people with the same birthday is nothing but finding a collision of hx, right? Because h of x is birthday, right? So basically, if you find 2 people with the same birthday, we are actually finding a collision of hx. So this algorithm that we've described, algorithm 5.3, has success probability half when q is equal to 23, right? Because we are doing those many queries, and total, m is 365 actually, right? So basically, we will be able to solve this, right? So now actually we have a general result for x naught to be a subset of x with q queries here. The success probability of algorithm 5.3, which I showed to you, the collision algorithm, epsilon is 1 minus m minus 1 by m times m minus 2 by m dot 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 m minus q plus 1 divided by m. The proof is straightforward, so I'm just showing you. If x naught is a x1, x2, xq, for each I, ei is the event, hxi is not member of hx1, hx2, hxi minus 1. So basically, these are the hash values of each point, right, up to I minus 1. And hxi is not member of this. So, probability of E1 is 1, and then we can compute this probability. EI condition, E1 meet up to EI minus 1 will be m minus I plus 1 divided by m. Okay. Now, so this whole probability from E1 up to EQ will be m minus 1 divided by m times m minus 2 divided by m, and so on, m minus q plus 1 divided by m. So probability that there is at least one collision will be 1 minus the whole thing, which is 1 minus the probability of this, right? So in fact, I can compute certain specific values here. So the probability of finding no collision is, we delete 1, so we are left, we are left with this. If you see here, m minus 1 by, so m, which is 1 minus 1 by m, 1 minus 2 by m, and so on. right? So we have 1 minus 1 by m, 1 minus 2 by m, and so on, 1 minus u minus 1 by m. So I can just take the product, and now I do this approximation. So we know that e raised power minus x is something like this series x approximation. So e raised power x is equivalent to 1 minus x. So 1 minus I by m, I can replace it by equivalent to e raised power minus I by m. With product, this goes into the summation here, e raised power minus this, right? So this is nothing but e raised power minus q times q minus 1 divided by 2m. Therefore, the probability of finding one collision will be 1 minus this quantity, right? Okay, which is obviously true, right? So now I can actually solve this for q. So epsilon is equal to 1 minus e raised power minus q times q minus 1 divided by 2m. After some simplifications, it turns out that q square minus q is equivalent to 2m times log of 1 minus epsilon. Now again, ignoring q is equivalent to square root of the whole thing, right? So now we have a rough approximation. Basically, if epsilon is 0.5, q turns out to be 1.17 times square root of m. Okay. So now with these numbers in hand, I can say that. So having just over square root of m random, queries, yields a collision with the probability of 50%, right? So actually, with m is equal to 365 and q is equal to 22.3, probability is at least half. So basically, we can say that what kind of security we can have. A 40-bit message address would be, insecure, right? Collision will be found with probability, p is equal to 1 by 4. If you do these many queries, 2 raised to 20, so it's a million random queries, So keeping these ideas in mind, SHA-1, the message digest has 160 bits, that gives you 2 raised to 80. Okay, so which is a big number actually, right? So you can say that safely we are safe. In fact, yeah, so I think I have another number I can tell you. Yeah, so SHA-3 has message digest between 224 bits and 512 bits in length. Okay, so if you take 224 bits or 512 bits, so we are, safe. Okay, so we can compute from these approximated formula how many queries are required, right, to actually break it. So okay, so basically this is something very basic thing. Now, after analysis of these things, I am skipping one proof actually, which is given in the book, of course, but collision resistance will imply pre-image resistance and second pre-image resistance under certain assumptions. Okay, so it is for us, if you are designing a hash function, I will make sure that it is collision resistant, and we are done. Okay, so that is the key idea. The proof is given, but I am skipping that. That proof here. Okay, so I think now I am ready to describe you general method for iterated hash function. So what is iterated hash function? So basically here the take home thing is that given a hash function, we should worry about the collision resistant. Okay, and that we can just check, how many bits we require minimal, so that we know that it is secure. Okay, so birthday paradox cannot happen here. Okay, so now we are talking about iterated hash function. So here h will, if you look at in the previous case here, so x is a set of possible and y, here h is basically having a finite domain, right? If x is finite, so basically if it is infinite, then we talk about iterated hash function. Okay, so let me talk about iterated hash function. Yes, so h will have infinite domain, So input and output of H are binary strings, fine. And this bar of X denotes, I mean, absolute value of X denotes the length of string X, okay. X and Y are binary strings of some length. Star means whatever length possible, And X double pipe Y means X concatenation of Y. That's a symbol. Concatenation of X and Y, two strings, okay. These are just basic assumptions. Let me now describe. Then we have a compressed function. So M plus T bits are compressed into M bits, okay. So here, a string of length M plus T is compressed into a string of length M, okay. And this iterated hash function H, I'm going to show you how we construct this. So it is kind of union of, so the 0 1 I means 0 1 raised to power I means binary string of length I, right? And then for each I we are varying from M plus T plus 1 to infinity, okay. It's a bit evolved thing. And this goes to a string of length L, a string of length L, binary string of length L, okay. So it requires certain steps. Step 1 is known as pre-processing step. So input string is X, and we assume that the length of X is M plus T plus 1, right? I mean, it's at least M plus T plus 1, right? Because that is the lower thing. Now construct a string Y from X, construct a string Y using a public algorithm such that length of Y is multiple of T, right? Length of Y is multiple of T. Normally we do it by padding, okay. So because X will have some size, right? So we want to make sure that it is multiple of T, okay, using some public algorithm. Now denote Y. So we assume that now Y is a multiple of T, right? So I can assume that Y is equal to Y1 concatenation of Y2 and so on YR. Each one is size T, right? Then whole thing will be multiple of T. From I runs from 1 to R. That is step 1. Step 2 is processing step. So this is pre-processing step. So pre-processing step, I have prepared a string Y, right? Which is a multiple of T. The length is multiple of T, okay? Now let IV denotes the initial value. So initial value, public initial value, that is bit string of bit string of length M. Now compute Z0 from IV. Z1 is basically compression of Z0 double pipe. So calculation of Z0 and Y1 and then compress it to Z1. Okay, so there are algorithms which we are going to talk about. Then we get Z1 is taken here, connected with next Y2, and that goes to Z2 and so on, Z2. Finally, you get ZR, which is compression of ZR minus 1, calculation of YR. Okay, so this is our general method for computing the processing. So here is a picture. I think I might be having a picture here. Here it is. So initial value. So Z0 Y1. Okay, so Y1 is there. Z0 is there. Combined, compress, you'll get Z1. Again, Y2 is there. You concatenate it. Then again compress to Z2. Y3 is concatenated. Then again compress and so on. Here we get YR. Finally, we get ZR as a output. Okay. So G of, again we use some function G, which is G of ZR is equal to H of X. This is our actual hash function. So step 3 is about this G function. This is an optional step. So output translation. So basically G is taking a string of length M and giving a string of length L using a public, it's a public function. So if Hx is equal to G of ZR, right? If G is not used, Hx is ZR. That is our output. Okay, because this is optional, so if G is used, obviously H of X is G of ZR. So basically, at this step here, this output ZR, we apply a public function G, and then we get the HX. Okay, this is the general technique of the compress function. Okay. Okay, so now string Y, how do we prepare the string Y in step 1? So basically from X, because we remember Y is a string of length multiple of T, so we do the padding function, padding of X, right? So using some padding function. So normally we attach zeros, right? Pad with zeros, right? So that this length is multiple of T. Also, we want to make sure that X going to Y is an injective function. This is also an important one. Okay, I think so. This is basically the whole algorithm, and I guess I'm not going to describe probably today because I hope you can see what is going on here, right? So we are going to explain it uh, in the next class. Okay, so that's all, I think. It involves a couple of other things. So basically, this is a popular method.